Hi, everybody. This is section 7.6, moments and center of mass. There's a lot of slides here, so I'm not going to look at all of them. I want to concentrate more on the formulas and then working out some problems using those formulas. You can go through, don't forget all these PowerPoints at the bottom of modules. You can go through this PowerPoint and look through this. It talks about finding mass equals force over acceleration. And if we have 1 pound of force with the acceleration of 32 feet per second squared, that's gravity. You can end up with pounds over foot per second square, which equals slugs. So let's look at the center of mass in a one-dimensional system. Basically, if you have a teeter-totter, and we're looking at this, and if you just look at this side of the teeter-totter is 2 meters, which is about 6 feet. This side of the teeter-totter is 2 meters. If this boy weighs 20 kilograms and this boy weighs 30 kilograms, it's obvious, since the distance, or that they're both the same distance away from the center, the balancing point, the fulcrum, obviously the teeter-totter is going to go down, and they show that it goes into a clockwise position. It rotates clockwise. It's not going around the circles, but it is going, the right side is going to be going down because the guy's heavier. That's pretty obvious. And you can look at the momentum. Left momentum was the mass times the distance. The right momentum is mass times the distance. If you notice, the right side has more momentum because he's heavier. It's the same distance. So if we introduce the x-axis line, a coordinate line, where 0 is going to be the fulcrum, we end up with this formula. The momentum about the origin is adding the mass times the distance together. And if we get, when we add all these up, if we get 0, then the teeter-totter is perfectly balanced. So if you get a momentum of 0, you can have a person over here and a person over here. It doesn't matter what the distance is and the weight, just as long, if the momentum equals 0, that means it's perfectly balanced. It's in equilibrium. So this is definitely one of the formulas I would write down. And we have it here. So definitely write this down. This is a one-dimensional system. And the center of mass is the momentum divided by the total masses. This is where you're just adding up all the masses along that axis. And this is the center. All right, so let's take a look at a problem here. Find the center of mass. Well, let's write down the formula. The momentum equals m1 x1 plus m2 x2 plus M3x3 plus M4x4. We have four masses here. M1 is 10 and it's located at -5 on the number line. M2 is 15 and it's located at 0. M3 is 5, located at +4. And M4 is 10, located at 7. So if I multiply these together, I get 90 minus 50 is 40. So my momentum is 40. Don't forget about the other formula. That's what we're looking for. This is what we're looking for, the center of mass, and that formula is MO divided by the total masses. MO is 40. We got it right here. And the total masses is 10 plus 15 plus 5 plus 10, which is 40. 40 over 40 is 1. So this is our fulcrum. So right here is where, at 1, that's where our fulcrum's at, and that's where the seesaw or teeter-totter, whatever you call it, is at equilibrium. Okay, that's not too bad. This is one-dimensional. And I think they go through, let me see if they go through this. Yeah, they go through the same thing I just did. All right, now two-dimensional. What if we're dealing with not just an x-axis like a teeter-totter there? What about an x and a y-axis? So we have masses in two-dimension. So we have two moments, one on the x-axis and one on the y-axis. Let's get to the formulas. Here we go. So this is the two-dimensional system. So to find a moment about the y-axis, it's m1 over the x value, m2 over the x value, just adding them all up. To find a moment about the x-axis, it's m, the mass times the y value, the mass times the y value, and adding those all up. The center of mass for the x-axis is right here, and for the y-axis is right here. And if you notice, they call it center of mass or the center of gravity. And don't forget, m is just adding up all the masses. All right, so we definitely need to write these formulas down. All right, let's go to a problem. Find the center of mass of system of the point of masses located at these points. Okay, so we are going to find my first. momentum of y. So don't forget the formula, it's x1. The formula was the mass of 1. Since we're doing y, then it's the x of 1 plus the mass of 2, x2, mass of 3, x3, mass of 4, x4, since there are 4 masses here. So if we look at mass of 1, its mass equals 6. The x value at that point is 3. The mass of number 2, right here, is 3. And the x value at that point is 0. The mass of number 3 is 2. And the x value is -5. The mass of number 4 is 9. And the x value is 4. When I do all this math, who knows what I get? I get 18 plus 0 minus 10 plus 36. 18 minus 10 is 8. 8 plus 36 equals 44. So we have one momentum. Let's try the other one. The momentum for x equals mass 1, y1, mass 2, y2, mass 3, y3, mass 4, y4. And once again, the mass of number 1 is 6. Its y value is -2. The mass of number 2 is 3. Its y value is 0. The mass of number 3 is 2. Its y value is 3. And mass of number 4 is 9. Its y value is 2. So I get -12 plus 0 plus 6 plus 18. 18 and 6 is 24. 24 minus 12 is 12. So there's the momentum about x. And we are looking for the center of mass. Is that what? Yes, find the center of mass. Okay, so for find the center of mass for the x-axis, you get my over m, and the center of mass for the y-axis is mx over m. Let's find the m's. Let's add up all our m's. When we add them up, m equals 6 plus 3 plus 2 plus 9. 11, 14, m is 20, looks like. If I add up all the masses, I get 20. My was 44. Masses is 20 and mx is 12. So if I reduce this, they both divide by 4. I get 11 over 5 for x bar. And for y bar, they both divide by 4. I get 3 over 5. So if you look at our center would be 11.535. 11.5 is like 2 1/4. 2 1/5. Let's see, right here. And 3/5, which is 0.6. So it would be somewhere around here. Let's see what they have here. got 11.5 and 3.5. So I'm going to clear this just to make sure. Looks all okay. 11.5 and 3.5. Yeah, everything looked fine. So it's that one coordinate, 11.535, which I showed once again. 11.5 is about right here. 3.5 is about right here. So this is the center of mass. And that's two-dimensional. All right, what if we're dealing with something more three-dimensional, like a plane with some depth, a planar lamina, a flat plate of material with constant density, and they call it a planar lamina. And if you notice, different shapes, and the question is on these planes, where is the center of mass? Where can you put a pencil on it and it will be balanced? So we do have some formulas here. They get to the derivation of the formulas that we need. Density, the mass equals density times the area. If you look at this, the moment is mass times distance, m1 times y, and they go through the whole process. This is what we need to write down. These are the two formulas we need for this section. We need these formulas, but we also need this mass. I would write down this mass formula also, sorry. This one right here. This is like a rectangle, density times height times width. Actually, where's the, this one right here. This is it, I'm sorry. This is the one I would write down first. If you look at this formula, if we want to find the center, let's say it's right here, this balancing point. We're going to do, once again, the top function, and this is the shape, it's the top function minus the bottom function. We're just integrating the top function minus the bottom. Remember, this is the bottom. The top does the whole thing. The bottom cuts this out. So we're just dealing with the stuff inside here. So it's the top minus the bottom. And we're integrating from A to B. That's the area. And then if we do the density, symbol for density there, we can find the mass using integration. Mass equals density times the area. So now I'd recommend writing these down. The moment about x, integrating the two functions divided by 2, and they were deriving that in the previous slides. So I would write this down. Now the moment about y equals x times the two functions subtracting, just because of the location. axis. And then we have center of mass, X part and the Y part. So we're going to write these down and then we're going to work on a problem. These are really important to make sure you have them written down correctly. You see here the functions added together here, the two functions are subtracted together. All right, let's take a look at an example. Find the center of mass of a lamina of uniform density bounded by the graph. So let's just take a look at this graph really quick. It's a parabola that looks like goes up to 4. And if you set 4 minus x squared equal to 0, you end up with x-intercepts at -2 and 2. X squared equals 4, square root both sides. X equals plus or minus 2. All right, so that's kind of the key, just knowing that you're going to integrate. It says, and the x-axis, so you're integrating from -2 to 2. We want to find the center of mass for this area here. And that's a 2. And this is kind of important to understand this also. The center of mass since this is symmetrical, it doesn't look symmetrical, but it is symmetrical. The center of mass for the x will be on the x-axis. Do you see the distance is the same? And since it's symmetrical, the center of the x-axis will be up here. We have to find out where now the y is also. So we know the center for the x is on the x-axis. In the center there. All right, so let's take a look what they do. Because the center of mass lies on the axis of symmetry, which is the x-axis, we know x bar, the center of mass for the x equals 0. You saw it's symmetrical and it's on the x-axis. So now the mass of the lamina, since we wrote that formula down, is density integrating from -2 to 2, like we said, with the function. Now, you saw in the formula that we had, the formula that we have written down was fx minus gx, but there's no gx. There's no second function, there's no empty spot. So it's just going to be the fx in this case. You know, if there was a function that did this and then this, and we were going to find this center of mass, then we'd have to take this function, subtract this function. But since it says the x-axis, there's no subtracting any function for it. We're finding the center of mass of all of this, so just one function. So that's kind of important to know. Okay, so to do this, you just integrate. This becomes 4x minus x3 over 3. And we integrate that from 2 to -2. And I want to put 2 in there. I get 8 minus 8 over 3. Subtract, put -2 in there. I get -8 plus 8 over 3. Let's see what I get when I get out of that. 8 minus 8 over 3. minus parentheses and -8 plus 8 over 3. And I get 32 over 3. So the density times 32 over 3. Don't forget, we have this density in front. I'm going to erase this. I'm going to write it down and make sure we're okay. If it lets me change out of this mode, there we go. (32 over 3 times the density. So they got the same thing I did. Now we need to find the moment about the x-axis. Place a represented rectangle in the region is shown, blah, 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 blah. If we go to our formula now, the moment about the x-axis, I should have wrote it down first, but I'm going to put it up here. This is one of those formulas we wrote down. Look at your notes. Mx equals the density integrating F plus G over 2, then F minus G dx. And so here's our F. And we didn't have a G. Remember, we're just doing the F. We didn't have a G because we're not subtracting the other function. So we just have F over 2 and then times F, and we're integrating from -2 over 3. So this is the formula we're using. Everything is the same. I'm going to take this 2 out over here. And I'm going to end up with, when I take that 2 out, I get 1/2 times the density. And I'm left with 4 minus x squared times 4 minus x squared. And you see, one's a plus and one's a minus, but we're just dealing with the F. This 4 minus x is the F. So there, I mean, that's why we're using the same, they both have a minus there because that's what our function is. We don't have the G, we're not subtracting that G. So before we integrate, we have to multiply. So when we distribute this, we end up with 16 minus 8x squared plus x4. Integrating from -2 to 2. So now we can integrate. But I do, yeah, everything looks fine there. 16x minus 8x3 over 3 plus x4, 5, add 1 and bring it down. So this is what I end up with. From -2 to 2. And we have a 1/2 p in front. All right, so I'm going to go to the next slide. I don't want to plug all that in, but I'm going to go to the next slide. Hopefully they did all the work for me. I'm sure they did. Yes, and when they did all that, when they integrated and then they multiplied by the density over 2, this is what they got. Okay, so now to find the y, the fulcrum of the y, the balancing point for the y-axis. It's mx over m. Mx we got right here is 256 over 15 times the density. And the mass we got earlier, 32 density over 3. If you remember. Like that, must have, oh, there it is right there. 32 density over 3. All right, and we put that on the bottom in the denominator. 32 times the density over 3. And the densities will cancel out. And when you do this amount, 256 over 15 divided by 32 over 3, we get 8 over 5. So they're going to show the momentum. Once again, the x, since this was perfectly balanced, do you see how it's symmetrical and the same as the x is going to be 0. The y we got 8 over 5. Right there at that point is its balancing point, the center of mass. All right, this was momentums and center of mass. I'm going to go to the homework now and try a couple problems there. Okay, so we're in the homework. Let's look at number 1. Consider a beam of length L. This whole beam is length L. You have 2 weights. Weight 1 is less than weight 2, and they depict that in the picture where the box for W2 is larger, so that is the heavier one. And we're trying to, if you read the instructions, it says find X such that this is an equilibrium system. In order to move a 600-pound rock, this is 600 pounds. A person weighs 250, this is 250. Once again, the higher one is W2. So if we look at our formula, momentum, and remember, we have to get momentum to equal 0 for it to be balanced. Your mass times your distance for the first weight plus your mass times your distance for your second place. And these two have to equal 0 when we look at this, hopefully. The mass over here for this first one is 250. Actually, we just have to set them equal to 0. These two have to be equal. We can just set these two equal, and then it will be balanced. The mass on one side has to equal the mass on the other. The momentum on one side has to equal the momentum on the other. 250 times x1, and our distance here is x. They labeled it as x. 600 times x2. And x2, they label it L minus x. If you look, And it says the entire beam is 5 foot long. That's the length that's L. So it's 5 minus X. So if you look, this whole thing is 5. This is 5 minus X, and this is X. So then we just distribute and set them equal to each other. 250X equals 3,000 minus 600X. Take this over to the other side and take this to the other side, and I get 850X equals 3,000 divided by 850 divided by 850. And it says rounded 3 decimal places. 3,000 divided by 850. 3.5294. It's just the X equals 3.529. All right. Let's see. That's what they got. Good. All right, let's try another one. Okay, next we'll do number 3 in the homework. Find the center of mass of a given system of a point. Mass is lying on the x-axis. So if we just look at a 2-dimensional X and Y, it says the center of mass is somewhere, I mean, I don't know where, but somewhere on the x-axis. In other words, the Y center is going to be 0 because it's on the x-axis. You see, it's the same distance for the Y. If it's on the x-axis, then Y equals 0. Any point on the x-axis, X is whatever it is, Y is always going to be 0. This point is going to be X something, but Y will always be 0. So the only thing we really need to do is for number 3 is find this. And if you go to 2-dimensionals, looking up that formula, it's my over m. And so first we need the formula for my in 2-dimension. That's finding the mass times x1 plus the mass times mass 2 x2 plus mass 3 x3. There's only 3 masses, so that's all I'm putting there. Mass 1 is 8, x1 is -5 from over here. Mass 2 is 3, x2 is 0, and mass 3 is 6, and this is 2. So this is -40 plus 0. I don't know why I'm putting, he's supposed to be multiplying these together. 0, and this is 12. So we get a my, looks like a -28. -40 plus 12 is -28. So that's the top. Now we just have to find the masses by adding the masses m1 plus m2 plus m3. m1 is 8 plus 3 plus 6. So the total masses ends up being 17. So once again, X bar, our center of mass on the x-axis, is my, which was -28, divided by 17. And so the coordinate for the center of mass is -28 over 17. and y is 0. Remember, we said it's on the x-axis, so the actual coordinate for the y part is 0. Okay, so that's problem 3. Okay, on this last problem that I'm going to do question number 7. Okay. We're going to look at the picture when we do question 7. It says find the momentum of x, momentum y, and their equilibrium point. And for the lamina, uniform density, and they give us 2 formulas here, x equals y plus 12 and x equals y squared. So these are the 2 functions. You can call them f and g, whatever we want to call them. Okay, so I'm going to scroll down to the actual picture so you can see. I'm not going to actually do the problem. I'm going to talk you through this. I'm going to talk, since all the work is here already, and there's a lot. I don't know how much room I have. I want to talk you through this function. So if you look at this, if we want to find, first of all, the area of this curve, there's 2 curves, and part of it falls below the x-axis. If you look at this, then the only option is to rotate this around to the left. We're going to take this with respect to y, because now y-axis is your bottom axis. You can even call it your x-axis. Do you see, if I rotate this this way, this graph becomes like this. This is the y-axis now. And this becomes the x-axis. If I could try to draw it, it goes from 3. If you is that 3 or is that 4? That's 4. So it goes from 4 to -3. So it goes from 4. If I try to look at it, it looks kind of like, I think it looks like this. There we go. And then it looks like this. There we go. So it looks something like that, right? This is the graph that we're talking about. So this is the top. Remember, we have to do the top function minus the bottom function. The top function, with this is y plus 12. And the bottom function is the parabola. Right, it wasn't just one of the functions of parabola. Yeah, just x equals y squared. So function g is y squared. So we're going to do the top function minus the bottom function. Here's the top. And then we're going to subtract the bottom part to find the area in here. All right, so that's where we're doing the top. It's supposed to say top minus the bottom. So if we go to all our functions, all our formulas, go to your planar lamina formula, and I'm going to write them down. The ones that you should have wrote down: mass equals the density F minus G. There's a mass. F was the top, once again, top minus the bottom. The top was y plus 12. and the bottom was y squared. And we're integrating this from -3 to 4, if you look at that. So that's the M, the total masses. And you see they go through it, and this is what they get. Next, we need to find mx. And our formula is the density, integrating the two functions added divided by 2, and then top minus the bottom. So if you look, here's our two functions divided by 2, and here's our two functions subtracting. Adding the two functions and dividing by 2 and subtracting the two functions. What they did then, they distributed all this stuff together. You know, they distributed this. I mean, take this 1/2 out. That's what they did here. And then they distributed it, combined like terms, and this is what they, there's a quick, that's the difference of squares. This plus that, this minus that, it's like a minus b, or a plus b times a minus b. So if you multiply these two, you get squared. You multiply these two, you get -4. But these two together and then a minus these two together equals 0. So those just cancel out. That's a nice quick problem. But then you have to go through and then integrate. So they integrate this, they added 1 and divided by 3. Here they added 1 and divided by 5. Plug the numbers in, and this is what they got. So I'm not going to go through all that process. You can see it right there. So we found my, the my. And then you can find the equilibrium point for the x-axis, because the x-axis, we have that on our somewhere, my over m. So this divided by this. And when you do that, you get 38/5. So that divided by or multiply the reciprocal. So it's this multiplying the reciprocal. You could divide the 2 or multiply by the reciprocal of the m. That's what they ended up with. You see the p's ends up canceling out. All right, so mx, look at the formula. Oh, that was, that was my, not mx. So mx, the formula is backwards when we're looking at the going back. Let me go. Oh, I wanted to go back to the book. I don't think I can. So the reason why, if you look at what we wrote down mx equals density integrating f plus g over 2, and then times f minus g. But that was all with respect to x. When we flip it and change it with respect to y, this becomes my. So that's why I think I mentioned mx at the beginning, but that was my, because we're with respect to y now. So the two formulas I wrote down, I said mx equals this, but that's when we respect to x. If we respect to y, then this becomes my. And mx is the opposite of what we had then. Mx is the my that we had because we're doing respect to x. So if you go back to your formula, the my formula is our mx formula, which is density integrating. It says x f minus g. Except we're doing this formula with respect to y. So it's y f minus g mx down here. So it's y f minus g. And we're still integrating from -3 to 4. So they go through the whole process, distributing, combining like terms. This is what we ended up with. Then you integrate, add 1 divided by 2, add 1 divided by 3, add 1 divided by 4, and then plug the numbers in and get this. Y prime, the center of mass for y is mx over m. Once again, here's the mx, and we did the m up here. Divide those two, and this is what you get. And there's our x, and here is our y. So the formulas changed from what we wrote down. And I don't have, I do have that PowerPoint back up. I'm sorry. There, I do have that PowerPoint. Where are those formulas? I want to show you just in case. So this is what I'm referring to. This is if we took respect to x. However, if we're doing it like we are in this formula with respect to y, mx becomes this formula and my becomes that formula because you're changing the axis. So you're actually flipping it. So the mx or the my, the mx with respect to y becomes density integrating y times f minus g. And then the my becomes the top one. Density integrating f plus g over 2 times f minus g dy. So these are the correct formulas, but if you change your integration from respect to x to respect to y, these two switch. This is with the dx, and these are with dy. You see how they just interchange each other. You could just switch these two when you do dy. All right, I hope that helped. Let me know if you need anything else. You guys have a good day.